let's talk about elements. I know that you've heard the periodic table of the elements. You've heard me use the word elements. For our definitions, we're going to say it's the same as an atom. If you hear the word atom, if you hear the word element, they mean the same thing. For our point of view, I'm not saying there could be some other situation down the road where you might have something going on different, but for us, if I say, here is an element of the periodic table, in your mind, you want to say, well, that's just a different kind of atom. That's a unique atom that we have listed on this thing called the periodic table. Common elements, you already know. We have oxygen, we have nitrogen, we have sodium, right, which goes into table salt, sodium chloride. We have argon, and we also have things like neon. You might see those neon signs, that glow orange or whatever, right? So we have all of these different symbols on the periodic table. We call it the periodic table of the elements. You could also call it the periodic table of atoms, because elements and atoms are the same thing. Okay, moving right along, we have discussed this before, but we're going to tie our, dot our I's and cross our T's right here. We have the idea of a compound, right? A compound is basically a molecule with two or more different elements. You might say, wait a minute, how's that different than a molecule? Let's go back to the definition of a molecule. That's why I wrote everything down. A molecule is a larger unit in which two or more atoms are joined, bonded together. And we gave lots of examples. So a molecule is anytime, a molecule is like the general class of what's going on. A molecule is anytime you have two or more things coming together in what we call bonding. Almost everything in chemistry we study is some sort of molecule. Not always, but very, very often, right? Let's give a couple of examples. All right, let's talk about CO2. This is carbon dioxide. One atom of carbon, two atoms of oxygen bonded together. Now, this is a molecule. How is it a molecule? Because it's two or more things that are stuck together. Anytime that happens, it's always called a molecule. But this is also called a compound. Why? Because these two elements that came together were different. When they're different, we call it a compound that comes together, right? What about the famous H2O, right? This is a molecule. I'm going to put little quotation marks. It's a molecule. It's also a compound because it's a molecule because it comes together two or more different things. And because they're different elements that come together, it's called a compound. What about the famous H2O2? You know what that is? H2O2 is hydrogen peroxide. You use that to clean cuts, right? It is a molecule because it is anytime two or more things come together. Notice we have four atoms here, two atoms of hydrogen and two atoms of oxygen. So it's four atoms here, but it's also a compound because it's different elements. So you might say, well, wait a minute, everything you've listed here is a molecule and a compound. So when can it be different? Let's talk about the oxygen molecule. Just call it O2, right? Well, this is a molecule because it's two or more things stuck together, but it's not a compound. It's not a compound, right? The reason it's not a compound is because it's the same element stuck together. It's only a compound when it's two or more differently named, different items that come together, then it's called a compound. These are different and they're stuck together, so it's a molecule and a compound. These are different. They're stuck together, so it's a molecule and a compound. These are different, so it's a molecule and a compound. These are the same atom, so it is a molecule, but it's not a compound, right? What about nitrogen gas, right? Same thing. It's a molecule and not a compound. What about chlorine gas? Well, it's a molecule, but it's also not a compound. So I just want you to remember, most of the time, things that we study are compounds. Because most of the time, the things you're studying are not the simple ones like oxygen gas or nitrogen gas, O2, N2, Cl2, H2, hydrogen gas. Usually, we're studying other things like methane or something like that with lots of different elements in there, so that we almost always call them compounds. But just so you know, it's only really a compound if the things that are made up of that molecule are different items. All right, and we're going to round out the tail end of this lesson by talking about mixtures. Now, so far we've talked about chemical reactions. We talked about things coming together, rearranging their electrons, rearranging their atoms, and coming out with a new arrangement, which we call the products or the outcome of the reaction. So that's chemistry, right? But we also have this other thing that we want to compare it with, which we call a mixture. In a mixture, there's no chemistry happening at all. It's just taking two objects and literally mixing them together, but nothing chemically is happening. So I'm not even going to write down the definition of this because I think it's easy enough to understand. It's basically when you have two or more items or samples of things mixed together that where no chemical reaction is happening. So examples of this, of mixtures. Well, before I give you examples, let me give you examples of the different kinds of mixtures, and then we'll give specific examples, right? We have two different kinds of mixtures. The first one is a homogeneous mixture. Homogeneous mixture, right? Homogeneous. Homo means same. Homogeneous mixture means that the mixture that you have has the same composition everywhere. Same composition everywhere. Right? So examples of this, right, would be something like salt dissolved in water. In water, the salt is dissolved, and the salt it doesn't disappear. It's just in between all of the water molecules that are there. And whether or not you take a drink of water, the salt water from the top, or if you take a drink of the salt water from the bottom, it's going to taste the same saltiness, because once everything is evenly distributed and dissolved, then we have the same concentration of salt everywhere. So that's called a homogeneous mixture. All of these solutions like sugar in water, salt in water, other things dissolved in water, they're going to be homogeneous situations. If you take sand with rocks and pebbles and you mix it up really, really, really good and you have a very uniform situation, no clumping, that's what we call a homogeneous mixture. But we also have the situation where it's not homogeneous, we have heterogeneous mixture. We have the heterogeneous mixture. So homo means same, hetero means different. So different composition in the mixture. So what we see here when we have a heterogeneous mixture is it varies in composition. So here I'm going to put, as an example, I'm going to put beach sand. Now you could mix the sand really, really well, but if you don't really mix it, if you take one scoop of sand from one part of the beach and then go 5 miles away down the beach and take another sample of sand, then the compositions are going to be a little bit different, right? Because the sand on the beach has not been mixed thoroughly. It's just deposited by the ocean, so it's going to be a little different. You're still going to have similar things going on, but it's not evenly mixed or evenly distributed, so we call it a heterogeneous mixture. Another example would be like rocks and dirt. Now, if I mix the rocks and dirt really, really, really well, if I pulverize the rocks to get it really uniformly distributed with the dirt, you could say it's homogeneous. But if you just throw some rocks in the dirt and do a little shaking, it's not going to be uniformly distributed. We call that a heterogeneous mixture. So we have mixtures which nothing chemically is happening. We just have two or more species coming together and mixing. And when you have these mixtures where everything's very evenly mixed, very uniform, we call it homogeneous mixture. Any kind of solution where things are dissolved or homogeneous, and then you have the heterogeneous mixtures where things are just clumpy and not mixed very well at all. Now, I want to wrap up this lesson with a conclusion, and I do want to wrap this up with a conclusion, and I'm going to do that now, but I'm going to give you a little bonus material at the end before I do that, because it's on my mind, and I don't want to forget to mention it. I'm sure I'll mention it, and we'll have entire lessons in the future, but while it's on my mind, I do want to tell you a few things. And I'm going to close by kind of giving you a roadmap as to what you really learn throughout chemistry from here on out to the next lesson all the way to the end of the road kind of deal. Before we do that, I want to go back to what we talked a minute ago. I talked about the electric force is millions and millions of times stronger than gravity. I keep harping on that because it really governs everything. It governs how the atoms how they start to share when they gain and lose electrons, and that leads to all the chemistry that we have. all of the chemistry that we have is all due to electrons moving around on the outer layers of the shells of the atoms that are mixed together. And sometimes they share electrons and sometimes they transfer electrons, and all of that sharing and transferring comes from the strength of the Coulomb force. That's called the Coulomb force, also called the electric force. And because of that, because all of the chemistry that we have is due to that, then all of the chemical bonding is also due to the strength of the electric force, right? So we're going to learn about single bonds, and we're going to learn about double bonds, and we're going to learn about triple bonds. And there are different strength of bonds, right? Some bonds, some chemical bonds are stronger than others, and the strength of the bond, it comes directly from how strong that electric force is, right? Right? And then I'm going to talk about the most important molecule in our world, which is called H2O. Now, the way we write H2O is 2 atoms of hydrogen and 1 atom of oxygen. Now, later on, we're going to get into this a lot more. We're going to have entire chapters on this later. But the way this thing is written is, or the way this thing, if you could zoom in on a microscope and see one atom, you wouldn't see a little letter here, H2 and O. You wouldn't see that. You would see something like this. You would see the oxygen atom in the center, and these 2 hydrogens would be off to the side, but it wouldn't be in a line. It turns out that the water molecule is actually bent a little bit, and I'll explain why in just a minute. But here are the 2 atoms of hydrogen and the single atom of oxygen. And this line that joins from here to here, and this line that joins from here to here, shows the idea that the oxygen is bonded to the hydrogen. And when we say bonded, generally it means we're sharing electrons. So there's other situations, we'll talk about it later, but usually we're sharing electrons. You might say, why are they sharing electrons? Well, you can't get too far ahead of me here, okay? We got to go crawl before we walk. The reason they share electrons is all because of that electric force is so strong. That is why. If you really get down to it, that's why. And also, there's a lot of quantum mechanics, which is way beyond the scope of this lesson, that gets into why atoms bond with each other. But for now, we have to crawl before we walk, and these lines are representing a single bond from here to this hydrogen and from here to this oxygen. Now, why is it bent? We're going to talk about why it's bent. We're going to have an entire chapter trying to understand what molecules look like when we actually draw them out, if we could zoom in and look at them. And some of them have weird shapes, and water is a bent molecule, right? The other thing that I want to impress upon you is that not all atoms attract the electrons with the same strength. It turns out that oxygen is an electron hog. It loves to attract electrons. And when I say it loves, I don't mean that it has a personality. I mean that the electric force is stronger on the oxygen to pull the electrons closer to it. So because of that, see, this line represents a sharing of the electrons between the hydrogen and the oxygen, and a sharing here between the oxygen and the hydrogen. But since oxygen is so much stronger at pulling the electrons that are here, they're actually not in the shared electrons are not like in the middle. They're pulled a little bit closer to the oxygen. These shared electrons here, they're not in the middle, they're pulled a little bit closer to the oxygen. So because of that, the oxygen has a little bit of a slight negative charge. And this little symbol is a Greek letter delta. It's a delta, and I don't care so much about what symbol you use. I just want you to focus on there's a minus sign here. And because the electrons are pulled this way and pulled this way, the oxygen, which normally would have a 0 charge, it's pulling the electrons a little bit closer towards it. Why? Because of the electric force. If you ever ask why in chemistry, it's almost always because of the electric force is so strong, okay? And because it's unbalanced and it's unequal in the sharing, then there's a teeny tiny more negative charge around this oxygen. And because of that, there's a teeny tiny a positive charge around this hydrogen, and a teeny tiny a bit of a positive charge around that hydrogen. Because you remember, when these come together, the hydrogen has its own electrons. This hydrogen has its own electron. These oxygen has its own electrons. When they come together, they share. You would think they would share right in the middle, so they're equally shared between the two. However, oxygen pulls the electrons a little closer, and it pulls these electrons a little closer. So if you zoom out and look at it, it appears that the oxygen has a slightly more negative charge than these hydrogens, which have a slightly more positive charge. So don't worry about the Greek symbol. Focus on that the hydrogens are very slightly positive, and the oxygens are very slightly negative. So normally, we don't talk about this for about 5 chapters into chemistry, or 6 or 7 chapters. This idea that the oxygen is a little more negative and the hydrogen is a little more positive, this is called polar. This means water is polar. Polar just means that one side of the molecule is a slightly negative charge and the other side of the molecule is a slightly positive charge. Now, why did I tell you this? Because this is just an introduction. I don't have to tell you this now. We're going to have an entire chapter talking about this, right? Why? Well, it's incredibly important that water is polar. I'm trying to give you motivation more than anything. I'm trying to get you excited. I'm trying to get you to be like, wow, that's neat. I didn't know that. Well, all the water you drink is very slightly negative on the oxygen and very slightly positive on the hydrogen. Now, why do we care about that? Well, because if I put salt in the water, the salt is also bonded together and it falls into the water. But you see, since part of the water is negative and part of the water is positive, this negative side is going to attract the sodium out of the salt. And the details don't matter, but one side of the oxygen is going to attract one side of the salt, and the other side of the hydrogen side of the water is going to attract the other side of the salt, the sodium chloride, and it's going to pull the sodium chloride apart. What do you think that means when sodium chloride gets pulled apart? It means it dissolves. So when you pour salt in a glass, I want you to start thinking microscopically what's happened. It's trillions and trillions and trillions of water molecules, which one half of which are positive, and the other half is negative. And altogether, it allows you, because the electric force is so strong, this tiny little charge imbalance on the oxygen, this slightly negative, can attract the positive part of the sodium chloride salt. And this tiny little positive charge on the hydrogen can attract the very slightly negative side of the salt. And because they're pulling on different ends of the salt, they pull the salt apart and they dissolve it. If you put sugar in, it dissolves the sugar. And water turns out to be able to dissolve a lot of different things. Why am I bringing this up? Because your body is mostly water. All the chemistry in your body relies on water. Why? Because all of the things that are happening that are important are dissolved in water. Your cell, all the cells of your body, they're basically chemistry, little bags of chemistry happening inside of water. And if water did not dissolve things, then you wouldn't be able to have liquid chemistry inside of your body. Nothing would work. Because when you have things floating around in a liquid, they can bump into each other and they can have chemistry with each other. When you have salt poured into water and it dissolves the salt, you have the salt broken apart, literally broken up into a sodium and a chlorine, sodium and a chlorine. We'll talk about ions later, but it pulls them into ions, which are just basically breaking them in half, but they're charged now, and they're floating around in the water. But in your body, that means everything can be floating around and it allows chemistry to happen, because when things are floating around, they can bump into other species and they can have chemical reactions. So if the electric force wasn't that strong, then water would not be a polar molecule, which means it wouldn't have a positive and a negative side. And if that didn't happen, then water wouldn't dissolve anything. And if that didn't happen, you wouldn't have chemistry for your body. And it also means ice wouldn't float, because ice also floats because of this charge imbalance. And I'll talk about that later, but it has to do with when you cool down water, it has to do with these charges on the hydrogens and the oxygens. They are what causes ice to form the structure that ice forms. It causes them to join up in a certain way to form the structure of the ice crystal. And that joining is what causes ice to float. And if ice didn't float, then a long time ago, all of the oceans would have just froze over from the bottom up, and there'd be no fishes and no life on Earth. So I guess I'm just trying to give you a little bit of motivation that something as simple as, oh, I tell you the electric force is so incredibly strong. Believe me, it's strong. And you're like, okay, I get it. But now I'm trying to give you a practical thing. If it wasn't that strong, then water would not have this charge imbalance. It wouldn't be polar. And if it wasn't polar, nothing would dissolve. And ice wouldn't float. And that means we wouldn't have any life in the oceans, because ice would be frozen solid. Because ice floats, it means when ice floats to the top, you could still have fish swimming on the bottom. But if the oceans froze from the bottom, then the whole thing just gets frozen solid, right? And you would never have any complex chemistry happening in a liquid vessel, which is what your body is doing all the time. So you couldn't have any respiration, you couldn't have any metabolism, and you wouldn't have any life. So everything literally comes back to how strong that electric force is. It's millions of times stronger than gravity. All right, I've done enough talking. I want to wrap this up. The last part of what I'm going to leave you with is a roadmap for what we're going to study in the future. We're going to study chemical compounds in detail. We're going to talk about when they combine, how they combine, and how do we name them? What do we call them? And how to determine what happens when we have two things coming together. Then we're going to talk about chemical reactions. When does a chemical reaction happen? Why does it happen? And what forms on the other end of a chemical reaction? And then we're going to calculate, okay, if I mix so many grams of reactants together, that's the things you mix in the test tube, how much grams of product am I going to get? Will it be solid, liquid, or gas that comes out the other end? And how many grams of it will I have, right? And then we're going to talk about how much heat comes out of that chemical reaction. Or sometimes chemical reactions require heat to get started. Like when you burn the log, nothing happens until you add heat. Some reactions don't happen unless you add heat to get it started. Some reactions are very, they liberate a lot of heat, like rocket engines, for instance. They liberate a lot of heat. So how much heat comes out of a chemical reaction? What is heat, by the way? It's a microscopic motion of atoms. So we're going to talk a lot about what heat is and temperature. Is light released? We're going to talk about what causes light to come out of a fire. It's the electrons jumping around inside of the atom, and they generate a photon of energy, which we call light, that comes out of that. So a campfire is heat and light. It's a chemical reaction, also with electrons moving, so we can see the light that comes out. Then we're going to talk a lot about the structure of molecules. So you can write these things down like H2O and CH4 and other things. You can just write them down with letters and numbers, but it doesn't tell you the structure. It doesn't tell you the shape. Why is water bent like this? It's not a straight line. That doesn't make sense. Well, it actually does make sense, but we have to dive into the details of what's happening. So we have to talk about electric structure. We have to talk about electronic structure around every one of these atoms. How are the electrons organized around the atom? And how do they interplay when two things come together? So we have to talk a lot about atoms and a little bit of quantum mechanics to understand how the electrons are structured around atoms and how they come together. We're going to talk about the chemical bonds next. Single bond, double bond, triple bond, and then all other flavors of bond called sigma bonds and pi bonds. How are the electrons coming together to make a bond? And what is a bond? And why do bonds happen anyway? Because believe me, that question is not as easy to answer as you might think. We're still studying exactly how bonds happen, right? Then we're going to talk about reaction rates. How fast does a reaction happen? How far will it go? How much heat is released and how fast will it happen? And then we're going to talk about gas laws, solid, liquid, and then we have the gas phase where we're going to have, what happens when you compress a gas? What happens when a gas expands? What kind of chemistry can you have with gases, if any? Right? And then we're going to talk quite a bit about solutions and intermolecular forces between the atoms and solutions. And then at the very end, we're going to talk a lot about quantum chemistry. In fact, you can go beyond this chemistry class to study an entire career in quantum chemistry. And that's all about what is happening around that atom. Why do the electrons behave the way they do? What is an electron anyway? And let me clue you in. An electron is not what I drew on the board. You see, a teacher told me a long time ago, my favorite teacher I've ever had in my life in university, he told me education was a series of lies. And it took me a while to understand what he meant, but what he meant is that I have to lie to you a little bit in the beginning so that you can understand something. And then as you understand more and more, I can tell you more truths so that you can make your own jump and make your own discoveries. So at first we tell you that atoms look like this, positive, negative electrons, they go round and round, but actually this picture is not right. So we have to talk about what do we really know about electrons. And I'll give you a hint. Electrons are little bitty waves. Protons are also little bitty waves. And even the light that you see are little bitty waves. So it turns out that I can summarize about 50 years of quantum research in the early 20th century by telling you that we pretty much figured out that everything is made of waves. Even the things that seem hard, they're really made of microscopic little waves. But we have to treat this education as a series of lies. We have to start somewhere, and then we have to build step by step by step so that you gain confidence as you go. And then we can get to the stuff down the line, in which case we run out of road, we have no more road, And you then have the tools to continue and build your own road and make your own discoveries. And that's the whole point of all this stuff. That's all I want out of this, is for you to learn and for you to move on and make your own discoveries. I hope that you've learned something from this introductory lesson. I tried to give you a roadmap. I tried to give you definitions. I tried to tell you some of the most profound things that I know about chemistry that can be explained in a few minutes. But everything we said here is really just the surface. We need to now go one level down below the surface. So watch this a few times if you need. Follow me on to the next lesson. We're going to continue our journey understanding chemistry. Learn anything at mathandscience.com.